Hello, I'm Levin. I'm working with my industry partner HDR on the topic that is the space games, competition and collaboration in multi-agent reinforcement learning for automated apartment floor plan generations. So for a research background, um, my problem is that about a space layout planning, which is over 60 years old. And throughout the years, mathematicians, architects, and computer scientists are trying to find the ultimate solution to this problem, which is the automated process of this problem. Um, but through our exploration, nobody has achieved the ultimate solution yet. They all needed minor manual adjustments at the end of their results for it to be used professionally. And I'm here with the uh, multi-agent reinforcement learning, which is a branch of reinforcement learning and a newly rising technique in machine learning. Trying to solve this problem by combining and using multi-agent reinforcement learning into space layout planning. So for the research question, how can multi-agent reinforcement learning be more efficient in numbers of layouts generated and accurate in realistic aspect of plans when applied to unit layout inside of a mixed-use residential building? So this research will be mainly focused in mixed-use residential building for investigation. For my aims, the three parts: efficiency, optimization, and realistic factor. And for efficiency, first thing comes to mind is that uh, the agent must acquire the full 100% area that the floor plan gives. So no, there will be no empty areas left. And secondly is the time that you use to generate one successful plan. For optimization, 70% of the unit area will receive solar access in winter, and each agent will need to occupy at least one cell next to the corridor for corridor access. Third is the realistic factor. As you can see from down below as a very simple outcome example, uh, I do understand that some of the floor plans will be interlocking with each other, but this is just to show a very basic understanding of the simple outcomes that we'll show later. And for a bit of the literature review, that what it comes to mind is that multi-agent reinforcement learning is a branch of reinforcement learning, which consists of a an environment and agents that in there with restricted actions. Uh, Unlike a supervised or unsupervised learning in machine learning, reinforcement learning develops itself within the environment. And the multi-agent part is that there'll be multiple agents in the same environment to work collaboratively and competitively. Just like the two GIFs that are shown here. This is a project by OpenAI using the game of hide and seek. As you can see, the blues are the hiders and the red ones are the seekers. The blue ones are trying to work collaboratively, hiding from the red one, utilizing the tools that they were given. And the red ones are trying to find the blue agents and utilizing the tools they were given competitively. Um, you may be wondering how is this related to a architectural floor plan problem. Now, if you can see the diagram below, it is a classic Atari game called The Snake. I believe most of people have heard of it. It is a game that um, the agent will try to eat the points and grow in itself. And what happened is that if I put multiple snakes into the same environment and they eat off the rewards or the solar axis points, they will grow in size and eventually it will become a fully grown floor plan and ready to use. For my workflow, it has around four parts: the input, the environment, the action, and the objectives. We talk about each part in details later. So for the input, the user is required to give a defined boundary of the floor plan and then input it into Rhino and Grasshopper to be divided into small grids, and then running the the grids into Ladybug for a solar analysis and producing the fully analyze the results for the user to pick a spot for their core block position. The core block consists of the elevator, the staircase, and the corridor. And then by putting all the data together into a CSV file to pass into a Python library called Tensho. For the actions, as you can see on the top half, this is the first action that each agent will be able to move. So yeah, we'll grow into 4 directions, and there's 2 versions. The second version is what I'm doing now, what I'm using now. Sorry. Uh, Comparing to the first version, it gets blocked by one cell. Just trying to grow to the right. The second one allows intersection, as it still grows to the right when uh, the cell that it tries to occupy is over 50% uh, blank. And the second half on the bottom is that the agent will be withdrawing the occupied cells from 4 directions. As you can see, a 2 by 3 shape occupied cells are allowed to withdraw horizontally and vertically, but a 1 by 3 will not allow to be withdrawn horizontally because it will cancel out all the occupied cells. So for the Tensho framework, it's where you putting all the environments and agents and rewards and rendering and everything together and get ready to train the agents. For the rewards function, the rewards function is based off the objectives. So no blank cells, 70% access of sun in winter, and at least 1 corridor adjacent cells occupied. And the rewards function consists of 3 parts: the number of occupied cells, so it doesn't exceed the maximum area, and less than the minimum area. Second part is the number of corridor access cells. Once again, each agent needs at least one corridor adjacent cells to be occupied for access to corridors. Um, Thirdly, the number of solar access cells. Uh, just what mentioned before is that 70% of accessing sun in winter is the objective that the rewards function is trying to chase. If it's not met, the agent will get punished. Application. Uh, Application is application. For some interesting results, as you can see, the top left corner, it shows a picture that throughout the training phase, and agent A is trying to bully all 3 other agents in the same area. As you can see, the final rewards are very negative. So that means that it's a very unsuccessful training session. By alternating my rewards function on, it produces the results on the right, and which shows basically all 4 agents gave up on growing itself and occupying blank cells, and it's very unsuccessful even comparing to the first one. As you can see, the numbers for the final rewards it's more negative than the first results. And for the final results and altered, I'd say it's the best result right now. You can see agency has learned its idea of size and solar axis for rewards, and it's by far the most amazing results I've seen from my environment for evaluation. Tensho is a very lightweight and beginner-friendly library, but it's only being published in beta in April this year, so it's very underdeveloped yet. Uh, so, and secondly, from results, agency developed its own standing of highest rewards, but it still requires more training for all the other 3 agents. Future development, training and visual adaptation. Firstly, refining the rewards function could make all three other agents grow as they intended to. Secondly, it was suggested by HDR, but I haven't implemented something like this yet. The viewpoint rewards. So when the levels gets higher and the view gets better, which means that the agent will acquire better view scores, and the price of that unit would increase. And thirdly, as you can see from the results before, they were printed in consoles, not very pleasant to watch. And what I was thinking is that implementing this into a Grasshopper environment, so the the results could be more clear. And thirdly, and final, shifting from potential to RL Lib. RL Lib is a much more developed library in reinforcement learning, so it could solve the current problem. And yeah, that's it. Thank you.